Welcome to G Fun Facts Online. The Earth is a celestial target, continuously drifting through a cosmic shooting gallery. For billions of years, our planet has endured a relentless bombardment from space, yet the scars of these violent encounters are often erased by the very forces that make Earth habitable. Tectonic subduction, glacial carving, relentless erosion, and the persistent march of biology act as a dynamic planetary recycling system. Because of this, the terrestrial impact record is notoriously incomplete, particularly in regions dominated by vast rainforests and ancient, weathered cratons. South America has long been a missing piece in this global puzzle, boasting only a handful of confirmed impact structures. However, the geological narrative of the continent has been forever altered. Deep within the heart of Brazil, an extraordinary discovery has breached the surface, revealing the cataclysmic signature of a massive extraterrestrial strike that occurred approximately 6.3 million years ago. Researchers have unearthed the first confirmed tektite strewn field in Brazil and the whole of South America, ushering in a new era of planetary science. The remnants of this ancient cosmic collision are not giant craters or devastated landscapes, but rather small, aerodynamic pieces of natural glass known as geraisites. To truly appreciate the magnitude of this Brazilian discovery, we must first understand what tektites are and the apocalyptic conditions required to forge them. Tektites are not meteorites. They are not pieces of an asteroid or a comet that survived the fiery descent through Earth's atmosphere. Rather, tektites are born from the Earth itself, transformed by the unfathomable energy of a hypervelocity impact. When a massive extraterrestrial body, measuring hundreds of meters to several kilometers in diameter, strikes the Earth's surface at speeds exceeding 15 to 20 kilometers per second, the kinetic energy released is equivalent to millions of nuclear warheads detonating simultaneously. In a fraction of a second, the target rock at the epicenter is subjected to pressures and temperatures so extreme that it does not just shatter, it vaporizes and melts instantly. This superheated, liquefied terrestrial rock is then ejected upward and outward at hypersonic speeds, forming an expanding plume that punches through the Earth's atmosphere and briefly touches the vacuum of near space. As this molten ejecta travels along suborbital ballistic trajectories, it rapidly cools in the freezing temperatures of the upper atmosphere. The chaotic tumbling and atmospheric drag sculpt the liquid rock into distinct aerodynamic shapes like spheres, teardrops, dumbbells, disks, and complex twisted forms. Upon re-entering the denser layers of the atmosphere, the rapidly solidifying glass undergoes secondary melting, creating the pitted, intricately textured surfaces characteristic of tektites. Finally, these glassy fragments rain back down onto the Earth, blanketing vast geographical areas known as strewn fields. Despite the violence and frequency of impact events throughout Earth's history, tektite strewn fields are exceptionally rare. Before the Brazilian discovery, the global scientific community formally recognized only a few major tektite fields. There is the Australasian field, the youngest at roughly 790,000 years old and the largest, covering about 10% of the Earth's surface, though its source crater remains famously elusive. Then there is the Central European field, home to the roughly 15-million-year-old moldavites associated with the Ries crater in Germany, famous for their vivid green color. The Ivory Coast field is about 1.1 million years old, linked to the Bosamtwi crater in Ghana. The North American field, containing bediacites and georgiites, is around 35 million years old and originates from the Chesapeake Bay impact structure. Finally, the Central American field, discovered in Belize, dates back approximately 800,000 years, with the Pantasma crater in Nicaragua as a proposed source. The emergence of the Brazilian tektite field effectively adds a new, major chapter to this exclusive geological catalog, establishing a definitive impact-strewn field on a continent where such evidence was previously non-existent. The story of this field begins in the vast, resource-rich state of Minas Gerais, historically celebrated for its gold, diamonds, and complex geology. It is here that researchers first identified anomalous glassy stones that defied local geological explanations. Led by geologist Álvaro Penteado Crosta from the Institute of Geosciences at the State University of Campinas, an international team launched a rigorous investigation. Recognizing their unique origin, the team officially christened the newly discovered tektites geraisites, honoring the state where they were found. Since the initial identification, the scope of the discovery has expanded exponentially. Researchers collected over 600 distinct fragments. The physical diversity of these geraisites provides a masterclass in hypervelocity fluid dynamics. They range from microscopic glassy beads weighing less than a single gram to substantial fragments, reaching 85.4 grams and measuring up to 5 centimeters along their longest axis. Their macroscopic shapes are a direct physical record of their chaotic flight. The collection features perfectly rounded spheres formed by surface tension in freefall, elongated ellipsoids stretched by aerodynamic drag, and complex dumbbell shapes created when spinning molten blobs began to pull apart just before solidifying. To the untrained eye, a geraisite might look like an ordinary black stone or volcanic obsidian. They are characteristically dark, opaque, and heavily textured, with outer surfaces that are aggressively pitted, displaying numerous small cavities. These vesicles are the frozen remnants of volatile gas bubbles that aggressively boiled out of the superheated silica melt and escaped just as the material flash froze. But when backlit by a strong, focused light source, the seemingly impenetrable black glass becomes brilliantly translucent, exposing a haunting, grayish-green hue, a stark contrast to the bright emerald green of European moldavites. This unique optical signature is a direct reflection of its geochemical parentage. But how do scientists prove beyond a shadow of a doubt that these are impact glasses, and not just volcanic obsidian? The answer lies in the water. The Earth's crust is inherently wet. Magma formed deep within the Earth absorbs water, meaning terrestrial volcanic glasses like obsidian retain significant hydration, typically containing between 700 parts per million to as much as 2% water. Tektites, conversely, are notoriously and exceptionally dry. The cataclysmic energy of an asteroid impact superheats the target rock, instantaneously boiling off nearly all water and volatile compounds. When Krosta's team subjected the geraisites to rigorous infrared spectroscopy, the water content ranged strictly between 71 and 107 parts per million. This ultra-low hydration level is a smoking gun, chemically impossible for terrestrial lava and an absolute confirmation of an extreme hypervelocity impact. Further chemical dissection revealed a high silica composition, with silicon dioxide levels ranging from 70.3 to 73.7%, placing them firmly in the realm of acidic, felsic rock derivatives. Interestingly, they exhibit a combined sodium oxide and potassium oxide content ranging from 5.86 to 8.01%. This alkali concentration is notably higher than averages found in other major tektite fields, suggesting a unique specific mineralogy of the target rocks at the Brazilian impact site. Variations in trace elements like chromium, measured at 10 to 48 parts per million, and nickel at 9 to 63 parts per million, serve as crucial forensic clues. Because tektite melts form and cool in minutes, they rarely mix completely. These fluctuating trace elements indicate the original target material was a complex, heterogeneous mixture of rocks, and possibly hints at minute contaminations from the vaporized meteorite itself. Perhaps the most dramatic microscopic evidence is the presence of rare inclusions of lecitellurite. Lecitellurite is an amorphous, glassy form of pure silica. Unlike quartz, which forms distinct crystal structures over thousands of years, lecitellurite is formed when quartz grains are subjected to instantaneous temperatures exceeding 1,700 degrees Celsius or 3,090 degrees Fahrenheit. Such temperatures are virtually unattainable in normal geological processes at the Earth's surface. Finding lecitellurite frozen within the geraisite matrix is irrefutable proof of a flash melting event far beyond the capabilities of even the hottest volcanic eruptions. Establishing the exact age of this impact was paramount. The research team utilized argon-argon radiometric dating, a precise geochronological tool relying on the natural radioactive decay of potassium-40 into argon-40 over immense spans of time. When rock is melted during an impact, the pre-existing argon gas escapes, resetting the radiometric clock to zero. By measuring the precise ratio of argon isotopes trapped within the cooled tektite glass today, scientists calculated exactly how much time has passed. The analysis yielded 3 tight, clustered age groups, 6.78, 6.40, and 6.33 million years ago, all with a tiny margin of error of 0.02 million years. These dates are entirely consistent with a single massive impact event. The slight variance is a known phenomenon where older dates represent samples that retained a microscopic fraction of inherited argon from the ancient target rock that failed to completely decay. Therefore, scientific consensus places the absolute maximum age of the impact at approximately 6.3 million years ago, firmly situating the cataclysm at the very end of the Miocene epoch. To fully grasp this event, we must rewind the clock 6.3 million years. The late Miocene epoch, specifically the Mycenaean age, was a period of profound ecological and climatic transition. Global temperatures were dropping, leading to the expansion of grasslands. Polar ice caps fluctuated, changing sea levels. South America was spectacularly unique, an isolated island continent before the Isthmus of Panama fully formed. The mighty Andes were undergoing intense uplift, altering weather patterns and driving the formation of the nascent Amazon River basin. The fauna roaming the Brazilian landscape would be unrecognizable today. Giant ground sloths, massive armored glyptodonts the size of small cars, and hoofed nodu ungulates grazed the savannas. The apex predators were massive, flightless terror birds, and marsupial saber-toothed sparacidonts. It was upon this thriving, highly specialized ecosystem that the sky suddenly fell. Without warning, a massive asteroid or comet entered the upper atmosphere at hypervelocity, compressing the air and creating an incandescent shockwave brighter than the sun. The intense thermal radiation instantly ignited forests and scorched the Earth for hundreds of miles. The subsequent impact triggered a seismic event that violently shook the entire South American tectonic plate. A blast wave of unimaginable force flattened landscapes, instantly vaporized localized river systems, and obliterated flora and fauna. Simultaneously, the hyperheated impact plume shot violently into the stratosphere, carrying millions of tons of vaporized continental crust. Within minutes, this plume cooled and condensed into the molten glass droplets we now call geraisites. Swept by high-altitude winds and the Earth's rotation, this rain of molten glass blanketed a massive geographic corridor, darkening the sky and raining lethal hot aerodynamic glass onto the survivors, setting secondary fires. Yet, one of the most compelling and frustrating mysteries surrounding this event is the distinct lack of a corresponding impact crater. Despite identifying the undeniable ejecta, Ground Zero remains stubbornly hidden. As Professor Crosta points out, this absence is far from unusual in planetary geology. Over 6.3 million years, heavy tropical rainfall and relentless river action could weather the crater rims down to ground level. Changes in local hydrography could have turned the crater into a basin that filled with millions of years of sand, clay, and organic matter. The dense canopy and thick undergrowth of the Brazilian landscape are incredibly efficient at hiding geological anomalies from satellite imagery and aerial surveys. However, the geraisites carry an internal atomic map pointing directly to the impact's location. Through complex isotopic geochemistry, researchers analyzed the specific isotopic signatures locked within the glass, acting as a barcode for the original target rock. The data revealed that the molten material originated from deeply ancient, felsic, granitic continental crust, dating back roughly 3.0 to 3.3 billion years, placing it in the Archean eon. This drastically narrows the search area to the São Francisco Craton, an old, stable block of the Earth's lithosphere dominating eastern Brazil, encompassing much of Minas Gerais and Bahia. The perfect match between the tektite melt and this 3 billion-year-old craton strongly suggests the crater is hiding somewhere in the vast expanse of the Brazilian highlands. Initially, the discovery was localized to a modest 90-kilometer strip in northern Minas Gerais. However, further field expeditions expanded the known boundaries of the strewn field exponentially. Specimens were recovered in neighboring Bahia and pushed further north into Piauí, extending the confirmed distribution of the Brazilian tektite field over 900 kilometers. A strewn field of this immense scale requires extraordinary kinetic energy to eject heavy molten glass across such vast continental distances, underscoring the violence of the 6.3 million-year-old event and suggesting the hidden crater will be a structure of formidable dimensions. The validation of this field is a paradigm-shifting event for South American geology. Globally, the Earth Impact Database recognizes over 190 confirmed impact structures, heavily representing North America, Europe, and Australia. South America historically contributed only about 9 formally recognized large impact structures, mostly hundreds of millions of years old. This underrepresentation is an artifact of preservation and exploration bias caused by dense rainforests and rapid geomorphological change. The discovery of the geraisites shatters this bias, filling a critical gap in the continent's geochronological record and validating the hypothesis that many more impact signatures remain undetected. Tektites and impactites are likely far more common than believed, routinely unnoticed or dismissed as ordinary rocks or volcanic slag. The study of ancient impacts like this is not merely an academic exercise. It holds profound implications for the future survival of our species. Understanding the frequency, scale, and environmental consequences of hypervelocity impacts is the foundational pillar of planetary defense. By mapping strewn fields and calculating the energy required to create them, scientists refine impact models to better understand how Earth responds to cosmic trauma. Professor Crosta is actively engaged in scientific outreach to combat misinformation about meteor strikes and doomsday asteroids. Alongside his students, he manages the Planetary Defense Profile on social media, translating complex geosciences into accessible knowledge to educate the public on the real science of near-Earth objects. By bridging the gap between deep-time geology and digital communication, the violent legacy of the geraisites fosters awareness rather than fear. The confirmation of the Brazilian tektite field is a monumental achievement, elevating South America's profile in the global study of hypervelocity impacts. The hundreds of small, aerodynamic black glasses scattered across a 900-kilometer swath of Brazil are silent, frozen testaments to a day when the sky burned and the Earth melted. They capture a fraction of a second of cosmic fury, preserved for 6.3 million years. Yet, the ultimate origin point, the massive crater carved into the 3-billion-year-old bedrock of the São Francisco Craton, remains a phantom. Did the massive ejection cause localized extinctions among the bizarre megafauna? How many more cosmic scars are buried beneath the dense vegetation of the Amazon or the deep soils of the Cerrado? Science advances by refining its mysteries. The identification of the geraisites provides an indisputable physical map. The hunt is now on, utilizing advanced satellite gravimetry, ground-penetrating radar, and deep geological surveying. Until that crater is found, the Brazilian tektite field remains a brilliant, glassy puzzle, a profound reminder that the history of our planet is written not just by the slow, earthly forces beneath our feet, but by the sudden, catastrophic rocks that fall from the sky. Thank you for listening to G Fun Facts Online, and keep looking up.